So let's see if we can apply this new relationship between net force, momentum, and time. So in the previous example, we had a logging truck and a car that were both traveling at the same speed down the highway. And suppose that both were required to stop in a time of 10 seconds. We'd like to know what is the change in momentum of the truck and the car, and what is the force required to stop each one. So if you remember back, we had calculated the initial momentum of the truck to be mass times velocity, which was 375,000 kilograms meters per second. And then the momentum of the car initially traveling down the highway was 37,500 kilograms meters per second, which was 10 times less because the mass was 10 times less. So we want to figure out, what's the change in momentum when they come to a rest. So if they come to rest, then both of them have final momentums of 0. So if an object is not moving, it doesn't have any momentum because it doesn't have any velocity. So if I was interested in what the change in momentum of the truck and the car would be, well, change in momentum is final value minus initial value. For the truck, it would be 0 minus 375,000 kilograms meters per second. So the change in momentum of the truck would be negative 375,000 kilograms meters per second. And if I wanted to know what the force was, I know that this new relationship that I have in terms of Newton's second law says that the net force acting on an object is the change in momentum over the time. So I've got the change in momentum, 0 minus 375,000, and then divided by the time interval where I'm requiring this change in the motion, which is 10 seconds. So if I divide that, the 0 is irrelevant, right? And if I divide by 10, the amount of force required to stop that truck in 10 seconds is negative 37,500. And then I can go through the same process for the car. I would have to do the change in momentum, which would be 0 minus 37,500, and then divide by 10, and I get a negative 3,750. So it requires less force to change the motion of the car versus the truck. So if we think about why we're talking about momentum, both the truck and the car would actually have the same acceleration. They were both starting at the same initial speed, they had the same final speed, and the time interval where they stopped was the same time. So both of these vehicles experienced the same acceleration, but yet the force required to change that motion is different because the truck has a much larger mass. So by incorporating this idea of momentum, this quantity momentum, it's actually telling us a little bit more about the motion. Just knowing how fast the truck was going or how fast the car was going and wanting them to stop really didn't tell us how much force we were going to have to apply to do that, but momentum does. So why are these forces negative, right? We could ask that question. And the reason these forces are negative is because the object is slowing down. And so there's going to have to be a force that opposes the motion in order to cause these objects to stop. So if they were traveling to the right, both of these vehicles, let's say they both applied the brakes, well, the brakes would cause a force, frictional force, acting opposite the motion, and that force would be negative. So that's the reason that those values there are negative. So basically what we've learned is that we can write Newton's second law in terms of momentum and time. So net force is equal to the change in momentum over the time, where before we were writing it as mass times acceleration. They both still mean the same thing, it's just a different perspective. And we also know that we can rewrite that expression by multiplying both sides of this equation by time so that we get the change in momentum of an object is equal to the net force applied multiplied by the time interval that that force is applied. Well, when we define something called impulse-momentum relationship, it's based on Newton's second law, right here, written in this new way where we multiply both sides by time. And we can define the force, the net force, multiplied by the time as a quantity called impulse. And then on the other side of the equation, we have change in momentum. So the impulse-momentum relationship is basically just saying that the change in momentum is equal to the impulse on an object. Now, You might ask, why is it necessary to define something called impulse? It's probably not really that necessary. We could just use this expression right here. But if you think about the term impulse, what should probably come to mind is short time intervals, right? If you're impulsive, you do things quickly without thinking about them. So impulse typically refers to something where it's a very small time interval. The reason that that's important is because often we're interested in how the momentum changes over a very small time interval. So specifically during collisions, if you throw a tennis ball against a wall, its momentum changes. But the time interval that that force was applied is a very small time interval, right? It hits the wall, bounces right off. So although this is true for all times, we're typically interested in using this expression over short time intervals. And so that's where that term impulse comes from. But in general, the change in momentum over here is always equal to the impulse. So if you know one, you automatically know the other. And just again as a reminder, right, change in momentum is just the final momentum minus the initial momentum. So we have an example here where I have two blocks that are essentially identical to one another. And the idea here is that the greater the impulse exerted on something, the greater the change in momentum is going to be. So here I have a large impulse because of the large force that's acting on it, the first picture. Or I can have a large impulse because I have a smaller force, but the time interval is larger. So when we think about impulse, we have to think about both the force being applied and the time interval. And so the first picture might look like I would have a greater change in motion because there's a greater force, but that force is applied over a shorter time interval. So the change in momentum of this block would be 10 times 1. It would be 10. The units would cancel out for newtons, and the seconds would give me kilograms meters per second. And if I look at the same situation down here, the impulse would be the force, which is 1 times the time, which is 10 seconds, and this would give me the same exact impulse, because impulse depends on both the force applied and the time. But more importantly, both of these blocks would actually have exactly the same change in momentum over the time intervals that are defined. So if these both started from rest, after 1 second, the first block would have exactly the same velocity as the second block after 10 seconds because they have the same change in momentum, both starting from rest. They'd both have the same final momentum after the time intervals that are given. So impulse depends on both force and time. You can have a large force or you can have a large amount of time and have a large impulse. So this is just a quick question to see if we're following what's going on. So I have two identical blocks that are pushed across the floor for the same amount of time. So now the time is the same. Block 1 is pushed with a force of 20 newtons. Block 2 is pushed with a force of 40 newtons. Which block has a greater impulse? So we know that impulse is force times time. We know that they both have the same amount of time, so the t here is the same for both. So whichever object experiences a greater net force will also have a greater impulse, and block 2 has a greater force applied, same time interval, so it will experience a greater impulse. This is exactly the same question, and now same amount of time, same blocks. Block 1 has a force of 20, block 2 has a force of 40. Which block has a greater change in momentum? Well, impulse is equal to change in momentum. So we discovered from the last example that block 2 had a greater force applied, therefore had a greater impulse, and as a result, the impulse is equal to the change in momentum. Block 2 will have the greater change in momentum. So impulse and momentum are directly correlated with one another. If the impulse is bigger, the change in momentum is also going to be larger. So now this one is a little more specific. Two identical blocks are pushed across the floor. Block 1 is pushed with a force of 20 newtons for 10 seconds. Block 2 is pushed with a force of 40 newtons for 5 seconds. Which block has a greater change in, this actually should say greater impulse change in momentum. So here they don't have the same force applied and they don't have the same time interval. So I have to be careful and I have to think about this in terms of the impulse momentum relationship. So for block 1, the impulse is the force times the time. So 20 times 10 is 200 newtons times seconds, which is the same thing as 200 kilograms meters per second. And so its change in momentum would be 200. And if I look at block 2, the force applied is 40 newtons and the time interval is 5 seconds, so that's also 200 kilograms meters per second essentially. So both would have the same impulse and the same change in momentum because impulse is equal to the change in momentum. So I mentioned earlier that when a tennis ball hits a wall, that the force that's being exerted on that tennis ball when it's interacting with the wall is over a very short time interval. And so that's part of the reason that we talk about impulse. And that occurs lots in sports, right? So the duration of contact is very small. So in a golf swing, when the golf club actually hits the ball, it's a very short time interval that they're in contact with one another. The golf ball's initially at rest, and then it leaves the club at a very fast pace. Same thing with a baseball player hitting a ball, and so on. So it turns out that this impulse-momentum relationship can actually be used to determine the average force exerted on an object. So if we know how the momentum changes when the object is struck, and we know approximately the time interval that interaction is occurring, then we can use that to figure out the force that's being applied, or the average force. Because when this club hits that golf ball, the golf ball is actually deformed a little bit. And so that force that's applied is not a constant force. It's actually a force that varies with respect to time. So this impulse-momentum relationship allows us to figure out what the average force is during an interaction by measuring the change in momentum and then the time interval of that interaction. All right, so here's another example. This is from the Hewitt textbook. So suppose that you had a car, or a truck in this case, and it's out of control. It's better to hit a haystack as compared to a concrete wall. And of course, the physics reason is they both have the same impulse, right? So they have the same change in momentum, because impulse is equal to change in momentum. So both, here's the truck, both cases, same mass, same initial speed, initial velocity. The end result is also the same. They both come to rest, so the truck stops here and the truck stops here. So they have exactly the same change in momentum. But by extending the hitting time, it reduces the force, right? So this impulse-momentum relationship is they have the same change in momentum, but hitting the hay, the time interval for stopping because of hitting the hay would be large, and a large time implies a smaller force, right? Because this is on the bottom, so if the time gets bigger, the force gets smaller. And then hitting the wall, you would go from traveling very fast to basically coming to rest in a very, very small time interval, right? And so that force would actually be very large. So this picture is showing small f, big T, right? And over here, big force, small time, but these are actually equivalent to one another because the impulse is the same, right? The change in momentum for both of these is exactly the same. So suppose that I have a dish. And will the change in momentum be less for this dish if I drop the dish and it lands on a carpet versus if it landed on a hard floor? So we're talking about the change in momentum. So when the dish falls, just before it hits the carpet, it's traveling at the same speed as just before it hits the hard floor. And we want to know, eventually when it hits the carpet, it hits the floor, they're going to come to rest. So will the change in momentum be less or greater for the carpet versus the hard floor? And I think most people would get this one wrong because you're thinking about the end result. So the dish, if it hits the hard floor, might break, but if it hits the carpet, it may not. So we have to be careful. This is asking for, will the change in momentum be less if it hits a carpet or, compared to the hard floor? And the answer is no. The change in momentum will be the same. So in both of these cases, hitting a carpet or a hard floor, the dish has the same initial velocity just before hitting the floor as it does when it hits the carpet. And then it has the same final velocity. They both come to rest. So the dish has the same initial velocity, the same final velocity. This means that the change in momentum is exactly the same for both, because momentum depends on mass and velocity. So they both start with the same initial velocity and end with the same velocity. Now, even though the change in momentum is the same and the impulse, the force exerted on the dish will not be the same. The dish actually will change momentum in a much shorter amount of time when it hits the floor, and thus the force would be greater on that, right? So when it comes into contact with the floor, it's going to change momentum very abruptly. So this is very similar to the last example with the truck hitting the haystack or hitting the wall. In both cases, the change in momentum was the same, but the end result of the force was different. So these are just a lot of the same types of examples. So if you're jumping from some height, you're better off bending your knees during impact with the ground because you're going to feel less force on your joints because you're extending that time frame from when you're changing velocity when you sort of give with the impact. The same thing is actually true if you think about how car airbags work. So those car airbags are designed to slow your stop over a greater amount of time when your body actually is moving forward. That airbag is sort of slowing you down over a greater amount of time versus sort of an immediate impact, and that's what causes less damage. Same thing is true when they say that boxers try to roll with the punches. So if you're going to be struck, it's better to sort of give with the punch because you're changing your motion over a greater amount of time versus just trying to stand very firm and not give with the punch. You're going to get a greater amount of force because the time interval of that interaction is shorter. So we have one last example. So we're at a birthday party and children are asked to participate in an egg throwing contest. And maybe some of you have done that before, where you stand away from one another in teams and you throw the egg back and forth, or a water balloon, for example, and you try to catch it so that it doesn't break, and then you keep walking further apart. So a team must throw the egg back and forth and then increase the distance. The eggs are exactly the same. So the eggs all have the same mass. And we're going to assume the mass of the eggs is 0.25 kilograms. All the teams are throwing the eggs with the same speed, and the eggs are traveling at approximately 4 meters per second just before being caught. So basically, the person throws the egg, the other person on the team catches the egg. Right before they catch the egg is traveling at 4 meters per second, and then they catch the egg and the egg comes to rest. So team A is catching the egg so that their egg comes to rest softly over a time interval of 2 seconds, while team B does not allow their hands to give as much and catches the egg in 0.5 seconds. Which team's egg is more likely to break? Why? And how much force does each egg experience when caught? So remember that the eggs have the same mass, the same initial velocity, same final velocity of 0, so the eggs for both teams experience the same change in momentum or the same impulse. So if the impulse is the same for both, the team that lets the time interval be larger should have a smaller force exerted on their egg, and the one that has the shorter time interval should have the larger force exerted on their egg, and thus the one that's more likely to break is team B. So let's see if we can calculate that force for each one. So I can calculate the change in momentum for both teams. So the change in momentum is just the final momentum, which is mass times final velocity, minus mass times initial velocity. And the initial momentum, the final momentum is 0, and the initial momentum is just 5 times 0.25, which is just 1. Subtracting that. So the change in momentum for both teams' egg is minus 1 kilogram meter per second. Now, if I want to find the force on the egg for team A, it's going to be the change in momentum over the time interval. And so the time interval for team A is 2 seconds, so minus 1 over 2 is minus 0.5 newtons. And if I want to find the force for team B, it's the change in momentum, which is the same for both, divided by the time interval, which is 0.5 seconds, which is negative 2 newtons. So team B will have a greater force exerted on their egg, and so their egg is more likely to break. The negative signs here, again, are just implying that this object is actually slowing down, so the force that's being applied to the egg has to be opposite the way that the egg is actually moving. So the impulse momentum relationship is very valuable. We can use it to figure out how much force is being applied, or if we know the force, we can use it to figure out how the motion is going to change. I forgot we had another question here. So Alice and Bob are traveling side by side in a straight line at 29 meters per second in identical cars. They both apply the brakes at the same time. Alice comes to rest in 30 seconds. Bob comes to rest in 50 seconds. Whose car experiences the greater impulse? Again, we have to be careful. Greater impulse. Impulse is equal to change in momentum. Both cars are identical. They're both traveling at 29 meters per second, so they have the same initial momentum. They both come to rest, so they both have the same final momentum, which means that they have the same change in momentum. If they have the same change in momentum, they have exactly the same impulse because change in momentum is equal to the impulse. So they both come to rest and they both have that same initial velocity and that they're identical. Same exact question, except whose car experienced the greater braking force? Now this is a different question. They have the same change in momentum, but they don't have the same time interval, right? So the change in momentum is the same, but the time intervals are different. So the object that comes to rest in a shorter amount of time, smaller time, bigger force. So Alice's car will experience a greater braking force.